Welcome, dear listener. You've found your way to Dreams of Gravity, and I'm so glad you're here tonight. Before we begin, I'd like to gently invite you to settle in. If you haven't already, go ahead and lie down, or find whatever position feels most comfortable to you right now. Maybe pull your blanket a little closer. Let your shoulders drop. Let your jaw unclench. Take one slow breath in through your nose and let it out softly. There's nowhere you need to be tonight. Nothing you need to do. You've made it to the end of another day, and that's enough. All that's left now is to drift slowly, quietly into the universe. And the universe, as it turns out, has been waiting for you. It's been waiting for quite a long time, actually. Roughly 14 billion years, give or take. So there really is no rush. Tonight, we're going to talk about something that genuinely surprised the scientific world. A galaxy that, by all rights, should not exist. A galaxy that broke the rules. And in doing so, opened a door to some of the deepest questions we've ever asked about space, time, and the nature of reality itself. But we'll get there gently. We always get there gently here. The universe has been around for nearly 14 billion years. It can wait a few more minutes while you finish getting comfortable and let the weight of the day begin to lift from your body. So let's begin at the beginning, or as close to the beginning as we can imagine. Close your eyes if you'd like, and picture this: absolute darkness. Not the darkness of a room with the lights off, where shapes still linger at the edges of your vision. True darkness. A silence so complete that even the concept of silence seems too loud for it. This is what the universe looked like in the very first moments after the Big Bang. Before light existed, before matter had gathered itself into anything recognizable, before there were galaxies or stars or planets, or any of the countless beautiful, strange things we're going to talk about tonight. The Big Bang. And the name is a little misleading because it wasn't really an explosion in the way we picture explosions. It wasn't a boom of fire spreading outward through empty space. It was more like space itself beginning to exist, like the very fabric of reality inflating from a single, impossibly dense point, smaller than an atom, smaller than a grain of dust, smaller than anything we have words for, and expanding outward in all directions at once. Not into something, just expanding. Creating space as it went, and time along with it. Before the Big Bang, in any meaningful sense, there was no before. Time itself was part of what began. In the first fraction of a second, the universe was unimaginably hot. Hotter than any star that exists today. Pure energy, vibrating and churning at temperatures so extreme that ordinary matter could not hold itself together. And then, as it expanded and cooled, because expansion causes cooling, the same way that air escaping from a pressurized container feels cold on your skin, that energy began to slow down, to thicken, to become matter. Protons and neutrons formed first, in the first few minutes. Then, over the following 300,000 years or so, the universe cooled enough for those protons and neutrons to capture electrons and become full atoms. Mostly hydrogen, with about a quarter helium and the faintest trace of lithium. Nothing more complex than that. The whole universe, in its earliest readable chapters, was a vast, warm, slowly cooling cloud of the three simplest elements in existence. And for a long time, hundreds of millions of years, that's all there was. A universe full of gas, quiet, drifting, cooling, waiting, Astronomers call this period the cosmic dark ages because there were no stars yet to light anything up, just gas, expanding slowly through growing darkness, gravity whispering through it all, patiently doing its invisible work. It reminds me of the moment just before sleep, actually. That soft, heavy stillness that settles over you when the day has finally let go, when thought begins to slow, when the edges of things soften, when you're not quite here and not quite somewhere else yet. The universe was in that place once, just resting in its own vastness before anything had decided to form, before any light had chosen to exist. A patience so deep it makes all other patience feel shallow. But gravity had other plans. Gravity is one of the most patient forces in nature. It doesn't rush. It doesn't announce itself. It simply pulls. Gently, persistently, endlessly. And in that early universe, where the gas was not perfectly smooth, but had tiny, quantum-scale variations in density, some regions ever so slightly denser than others due to fluctuations in the earliest moments of the Big Bang, gravity began to do what gravity does. It pulled those denser pockets together, slowly, over millions of years. The gas started to clump, the clumps started to grow, and eventually, in regions where enough gas had gathered into sufficiently dense cores, something remarkable happened. The pressure at the center of those clumps became so intense, so crushing, that hydrogen atoms began to collide with enough force to fuse together. Two hydrogen nuclei merging into one helium nucleus, releasing a burst of energy in the process. Then another fusion. Then another. A chain reaction that could sustain itself, because the energy it released pushed outward just enough to balance the gravity pulling inward. A delicate, magnificent equilibrium. A star was born. And when you think about it, when you really sit with the idea, every single star you have ever seen in the night sky is a nuclear furnace. A place where matter is constantly being transformed into energy, where hydrogen becomes helium and in doing so releases the light that travels across unimaginable distances to reach your eyes. The stars are not cold and distant and indifferent. They are burning, actively, furiously, beautifully burning. And they have been doing so for longer than life has existed on Earth. The light from some of the stars you can see on a clear night left its source thousands of years ago. It traveled through the vacuum of space, across distances so vast they barely have meaning, and it arrived right now, tonight, to reach you. That light is older than every human civilization that has ever existed. It crossed the cosmos and found you specifically on this particular night as you were settling in to rest. There is something in that worth pausing over. You didn't go looking for that light. It came to you. It traveled for centuries or millennia through the indifferent cold of space, and the moment it chose to arrive was this one. Coincidence, certainly, but a beautiful one. By the way, I wonder, where are you watching from tonight? Which city and what time of day is it for you right now? Are you curled up in bed with the screen dimmed low or lying outside somewhere under the actual sky? I think about that sometimes. All of you, in different corners of the world, different time zones, different weather, different kinds of darkness outside your windows, all somehow listening to the same story about the same universe. There's something quietly beautiful about that, a kind of invisible gathering scattered across the surface of one small planet, all looking up at the same stars. But let's keep going, because we've only just arrived at stars, and there is so much more ahead of us tonight. Stars don't live forever. Even the most massive, brilliant stars, the ones that burn hundreds of thousands of times brighter than our own sun, eventually reach the end of their fuel. And what happens when a star runs out of hydrogen to fuse? It begins to change, to evolve, in ways that range from quietly poetic to almost incomprehensibly dramatic, depending on how large the star was to begin with. A star like our sun, medium-sized, steady, middle-aged at about 4.5 billion years old, will eventually exhaust its core hydrogen and begin to swell outward. Its outer layers will puff up enormously as the internal balance shifts, transforming it into what astronomers call a red giant. Our sun will expand until it engulfs Mercury, then Venus, and quite possibly Earth as well, its surface extending to roughly where our planet currently orbits. But this will happen in about 5 billion years from now, a time frame so distant it makes all of human history look like a single heartbeat. There is no urgency in that fact, only scale. Only the humbling reminder that the universe operates on timescales for which we have no intuitive feeling, no emotional reference point. We can say the numbers, but we cannot truly feel them. And perhaps that's all right. When a red giant finally exhausts its remaining fuel, it doesn't explode. It gently releases its outer layers in a slow, luminous cloud of gas called a planetary nebula, one of the most visually stunning things the universe produces, glowing with colors that range from electric blue to deep violet to warm amber, shaped by stellar winds into spheres and rings and hourglasses and butterfly wings. Meanwhile, the star's core collapses into a small, incredibly dense object called a white dwarf. A white dwarf is roughly the size of the Earth, but contains roughly the mass of the Sun. A single teaspoon of its material would weigh several tons. It simply sits in space after that, slowly cooling over billions and billions of years, like an ember that will never fully go out, radiating the last of its heat into the surrounding dark, patiently becoming something colder and quieter than it ever was before. There's something almost peaceful about that image. A star that has burned for billions of years, finally growing quiet, releasing its last breath in a bloom of colored light, then settling into a long, patient cooling. Stars have their own kind of rest, their own version of what you're doing right now. But not all stars go quietly. The really massive stars, the ones that contain 10, 20, 50, or even 100 times the mass of our sun, those stars end differently. They burn through their fuel far faster, living brilliantly but briefly by cosmic standards, sometimes only a few million years compared to the sun's expected 10 billion. When they run out of fuel, they don't gently release their outer layers. They collapse so violently and so suddenly that the implosion rebounds outward in an explosion of almost incomprehensible scale. A supernova. For a brief period, days, sometimes weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. One dying star, radiating more light than all of its neighbors combined. It is the universe reminding itself and us just how much energy it contains, just how extreme things can get when matter is pushed far enough, compressed hard enough, and finally released. And supernovae matter for a reason that goes beyond their raw brilliance. They are the reason you exist. Every element heavier than iron in the universe, the calcium in your bones, the iron in your blood, the oxygen you're breathing this very moment, the carbon in every molecule of your body, the phosphorus in your DNA, the sulfur in your proteins, was forged inside a star and scattered across space by a supernova explosion. You are made of star stuff. Not as a metaphor, not as poetry, as a literal, chemical, physical fact. The atoms in your body were born in the cores of stars that lived and died long before our solar system even formed. Those atoms were scattered across interstellar space in stellar explosions, gathered over millions of years into new clouds of gas and dust, and eventually incorporated into the solar nebula from which the Sun and Earth and you were all made together. You have been part of the universe for a very, very long time. You are not watching the cosmos from the outside. You are the cosmos, watching itself. You are the universe having become curious about its own nature. Let that thought drift with you for a moment. You are not separate from all of this, looking up at it from a distance. You are part of it. A small, temporary, beautifully complex arrangement of atoms that the universe assembled out of itself. And now, in this brief and astonishing moment, those atoms are aware. They feel tired at the end of a long day. They seek warmth and rest. They find beauty in stories about the dark and the distant, and the incomprehensibly large. And that capacity for wonder, that ability to lie still in the dark and feel moved by the thought of a dying star, is perhaps the most remarkable thing the universe has ever produced. Now, let's talk about what's left when the most massive stars collapse. When a star with enough mass dies in a supernova, the core left behind after the explosion is so heavy, so compressed, that even the pressure of densely packed neutrons cannot hold it up against gravity. The core keeps collapsing, past the density of a neutron star, which is itself an extraordinary object, only about 20 kilometers across, but containing more mass than our entire Sun, spinning hundreds of times per second, with a magnetic field trillions of times stronger than Earth's, and into something that our physics can barely describe. A singularity, a point of effectively infinite density, wrapped in a region of space where gravity is so intense that nothing, not matter, not radiation, not light itself, can escape once it crosses a certain boundary. A black hole. The boundary is called the event horizon. And one of the most quietly mind-bending things about black holes is that from the outside, they don't look like much. They are invisible in the most literal sense. You can't see the black hole itself. You can only see its effects. The way it warps the light of everything around it, bending the paths of photons into curves, creating halos and rings of distorted light. The way nearby stars orbit something invisible, pulled by a gravitational source that emits nothing. The way gas and dust spiral inward toward the event horizon, heating to millions of degrees in the process, glowing brilliantly in X-rays and radio waves and visible light, a last frantic brilliance before crossing the horizon and vanishing from the observable universe forever. The first direct image of a black hole's shadow was captured in 2019 by a global network of radio telescopes called the Event Horizon Telescope, which linked observatories across the world into a single instrument the size of the Earth itself. The image showed a glowing ring of orange-gold light, heated gas swirling around the event horizon, surrounding a dark central region. That darkness was the shadow of the black hole at the center of a galaxy called M87, located 55 million light-years away, a mass 6.5 billion times that of our Sun. made visible for the first time in history. When that image was released to the world, there was something in the response of people everywhere that went beyond scientific interest. It touched something deeper, a sense of having seen something that wasn't supposed to be seeable. A door opened briefly into the most extreme place the universe contains, and people stood quietly in front of their screens and felt small and felt something they might not have had words for. A mixture of awe and recognition, as if they were seeing something they had always half known was there. And at the center of our own Milky Way, there is a black hole too, called Sagittarius, a star with a mass about 4 million times that of the Sun. In 2022, the Event Horizon Telescope captured its image as well. 4 million suns compressed to a point sitting 26,000 light-years from where you're lying right now. Quiet and invisible and immeasurably powerful at the very heart of the galaxy you live in. And now we arrive at galaxies themselves. Because stars are not scattered randomly across the universe. They come in families, communities, vast, slowly rotating collections of stars, gas, dust, and dark matter held together by gravity, organized into shapes of breathtaking variety. Elegant spirals with sweeping arms of blue-white young stars, smooth oval ellipticals that glow with the warm amber light of old stellar populations, irregular galaxies torn into ragged shapes by gravitational encounters with their neighbors, lenticular galaxies that sit somewhere between spirals and ellipticals, disc-shaped but without prominent arms. Each type tells a story about its history, about the mergers it has survived, the environment it grew up in, the pace at which it formed its stars. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars, depending on how you count. It is a barred spiral galaxy, about 100,000 light-years in diameter, its center dominated by an elongated bar of older, redder stars, from which two major spiral arms and several minor ones wind outward. Embedded in those arms are regions of active star formation, glowing blue with the light of newly born massive stars, threaded with dark lanes of obscuring dust, lit here and there by the warm glow of hydrogen gas clouds energized by stellar radiation. If you could somehow lift yourself out of the Milky Way and look down on it from above at a sufficient distance, it would look like a great, slowly turning pinwheel of light. The arms trailing behind the rotation like water behind a turning paddle. The central bar glowing warmly, the whole structure alive with motion on timescales, too long for any human life to perceive. We live about 26,000 light-years from the galactic center, in a relatively quiet section of one of the minor spiral arms, a neighborhood of space that is, by cosmic standards, rather calm and unhurried. Our Sun takes about 225 million years to complete one full orbit around the galactic center, a span of time astronomers call a cosmic year or a galactic year. The last time our solar system was in the same position relative to the galaxy that it occupies right now, the earliest dinosaurs had only just begun to appear on Earth. The time before that, there were no land vertebrates at all. Each galactic year is a chapter so long it contains entire evolutionary sagas. And right now, at this very moment, as you lie still and breathe slowly in the dark, you are moving. The Earth spins on its axis at over 1,000 kilometers per hour at the equator. The Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at about 220 kilometers per second. The Milky Way moves through the local group toward the great attractor at hundreds of kilometers per second more. Everything, everywhere, is in constant and layered motion. And yet, from where you lie, the night is perfectly, completely still. Both things are true at once. You are hurtling through space at speeds that would be incomprehensible if you could feel them, and you are also utterly, peacefully at rest. The universe contains both of these realities simultaneously, without contradiction. It always has. Beyond our Milky Way, the universe is populated with those 2 trillion galaxies, each one a world unto itself, each containing billions of stars. Many of those stars almost certainly hosting planets. We've now confirmed thousands of exoplanets in our own small neighborhood of the galaxy, and the statistics suggest that virtually every star in the sky has at least one world orbiting it. The number of planets in the observable universe is a number so large it dissolves into abstraction, like trying to count individual grains of sand, not just on one beach, but on every beach on every world that has ever existed. And on some fraction of those worlds, we genuinely don't know how large a fraction, the chemistry may have organized itself into something that could be called life. Something that metabolizes and replicates and responds to its environment. Something that might, over long enough timescales, look up at its own sky and wonder what's out there. We don't know if we're alone. We genuinely don't. The universe is old enough and large enough and chemically rich enough that life elsewhere seems not just possible, but to many scientists, likely. And yet, we have not found it. The silence from the cosmos on this question is one of the great unresolved mysteries of our time, and perhaps the most personally meaningful one. Are we the universe's only moment of self-awareness? Or are there other minds out there on distant worlds, lying awake at night, telling their own stories about the stars? And this is where our story takes its most surprising turn. In the years following the launch of the James Webb Space Telescope in late 2021, astronomers began receiving images and spectroscopic data that genuinely unsettled the cosmological community. James Webb, often called JWST, is the most powerful space observatory ever built. Its primary mirror spans nearly 6.5 meters, made of 18 hexagonal gold-coated beryllium segments that unfold in space with extraordinary precision, like a flower opening in the dark. It orbits the Sun about 1 million miles from Earth, at a gravitationally stable point where it can maintain a constant orientation and keep its instruments cold enough to detect the faintest infrared light from the most distant objects in the universe. Infrared light, light whose wavelength is longer than visible red, is essential for seeing the earliest galaxies, because the expansion of the universe stretches light as it travels. Light that was emitted in the ultraviolet by young, hot stars in the early universe arrives at us. Billions of years later, shifted all the way into the infrared. Webb was designed precisely to see this stretched ancient light. And when it did, it found things that didn't fit the map. Galaxy after galaxy in the very early universe, seen as they existed when the cosmos was only a few 100 million years old, were far too large, too bright, too structured, and too full of stars for the time at which they appeared. Our standard model of cosmology, carefully built and refined over decades, tested against observation after observation, supported by an enormous body of evidence, predicts that galaxies in the early universe should be small, irregular, and relatively dim. They should be the beginnings of things, the rough first drafts. The universe, in those early times, simply hadn't had long enough to build anything much larger. That was what the model said. But that is not what Webb found. One group of these objects was informally described by astronomers as impossibly early galaxies, a phrase that speaks volumes about the genuine surprise in the scientific community. These were not fringe detections. They were clear, unambiguous signals from large, bright, well-formed galaxies existing at a time when the universe should barely have had the raw materials in place to begin making them. Some of them contained as many stars as our own Milky Way, organized into recognizable structures, glowing with the integrated light of hundreds of billions of suns. All of this at a cosmic age of only a few 100 million years. In terms of the universe's total lifespan, that's like finding a fully grown tree that sprouted and reached maturity in the first few days after a seed was planted. A galaxy nicknamed the Sparkler showed clusters of ancient stars clinging to a young galactic body, like glittering ornaments on a young tree. Some of those star clusters, potentially among the oldest objects in the universe, formed in the very earliest epochs of cosmic history and somehow preserved intact to this day, orbiting a galaxy that should, by any conventional timeline, still be in its infancy. Other early galaxies showed signs of already having gone through multiple generations of star formation, meaning stars had formed, lived out their lives, died, and contributed their enriched material to a new generation of stars, all within a time frame our models suggested was barely enough for the first generation to have formed at all. The question these discoveries raised was not a small one. It was, and remains, one of the most actively debated questions in observational cosmology. What does it mean for our understanding of the universe if galaxies form this fast, this efficiently, this early? The honest and beautiful answer, the one that distinguishes science from dogma, is that we don't fully know yet. But we are asking, urgently, carefully, excitedly. Multiple research teams around the world are now working on revised models of galaxy formation, incorporating new assumptions about star formation efficiency in the early universe, about the behavior of dark matter under extreme early conditions, about the possible role of supermassive black holes in accelerating the growth of early galaxies. Some models suggest that the first black holes in the universe formed directly from collapsing gas clouds rather than from dying stars, may have grown to enormous sizes very quickly and then driven rapid star formation in their host galaxies through the energy they released. This process, called AGN feedback, can in some circumstances suppress star formation, but in others it may actually trigger it, compressing nearby gas clouds, pushing them past the threshold needed to collapse into stars. Others look at the data and wonder whether our assumptions about dark matter need revision at a more fundamental level. The dark matter particles move. Cold, dark, the dark matter particles move. Cold, dark matter, moving slowly, tends to clump on small scales first and build up to large structures gradually. Warm, dark matter would behave differently, potentially allowing large structures to form more quickly in some scenarios. The James Webb observations may, over the coming years, help us constrain what dark matter actually is. Not just what it does, but what it fundamentally consists of. And there is always the most radical possibility that our standard cosmological model, while enormously successful in explaining the universe on large scales, may be missing something important on the scale of individual galaxy formation in extreme early conditions. This would not be the first time a successful model turned out to be an approximation of a deeper truth. It would not be a failure. It would be science working exactly as it should. Observations pushing theory forward, theory making new predictions, observations testing those predictions, the cycle continuing indefinitely, the map of reality slowly becoming more detailed, more accurate, more honest. Let's pause here and breathe for a moment. Breathe in slowly. Let your chest rise and fall. Notice the weight of your body against the surface beneath you. Notice how your breath comes and goes without you having to think about it. Your body doing what billions of years of evolution shaped it to do, all on its own, without your direction. You can let a great deal happen tonight without your involvement. The universe will keep expanding. The galaxies will keep turning. The nebulae will keep building their stars. And your body will keep breathing. All you need to do is rest. Let's drift a little further now, because there are more wonders to visit before sleep takes you all the way down. Between the galaxies, in the vast, cold expanses of intergalactic space, there is not simply emptiness. The universe has structure on its largest scales that we've only recently begun to map with any completeness. Galaxies cluster together into groups and clusters, pulled by each other's gravity into associations that range from small gatherings like our own local group to massive galaxy clusters containing thousands of galaxies embedded in enormous clouds of superheated gas, so hot that they glow in X-rays. The Virgo cluster, the nearest large galaxy cluster to us, contains over 1,300 galaxies in a region about 8 million light-years across. The Coma cluster, farther out, contains over 1,000 bright galaxies and possibly tens of thousands of smaller ones, all held together in a gravitational embrace that has lasted for billions of years. Those clusters connect along filaments, long, thread-like structures of gas and dark matter stretching across hundreds of millions of light-years, linking cluster to cluster across the cosmos like the strands of an enormous web. Between the filaments are the voids, vast, nearly empty regions of space, hundreds of millions of light-years across, where the density of matter is far lower than the cosmic average. The universe, at its largest scales, has a texture like foam, like a sponge, like the inside of a loofah, walls and filaments enclosing hollow interior spaces, structure nested within structure at every level. When astronomers first fully mapped this cosmic web in detail, the visual similarity to biological networks was striking and immediate. It looks like a neural network, like neurons in the brain with their branching connections and clustered nodes, like mycelium spreading through soil beneath a forest floor, like the fine structure of a lung viewed under a microscope, or the branching of river deltas seen from very high above. Whether this resemblance reflects something deep about the mathematics of network formation, the same underlying equations producing similar-looking structures at vastly different scales, or whether it is simply a natural human tendency to see familiar patterns in complex data, is an open and genuinely interesting question. The cosmic web is real in any case. It is vast, it is intricate, and it is one of the most quietly majestic things the universe has ever organized itself into. Now let's visit the nebulae, because among all the objects in the cosmos, they are the ones that come closest to what I imagine the universe looks like when it is doing something gentle. A nebula is a cloud of gas and dust in space. The word comes from the Latin for mist, or cloud, or fog. And there is something in that etymology that feels right. Nebulae have a softness to them, at least in the images we make of them, that other cosmic objects don't quite possess. Black holes are dramatic, supernovae are violent, but a nebula is just drifting, glowing softly, becoming something slowly over millions of years. Some nebulae are the remnants of dead stars, the scattered material of stellar lives that ended long ago, still glowing with the energy left over from the explosion, or still lit by the dying core at their center. Others are stellar nurseries, regions where new stars are being born right now as you listen, where gravity is slowly pulling gas and dust together into the dense, warm cores that will eventually ignite and begin their long nuclear lives. And all of them are shaped by the interplay of gravity and radiation and stellar winds into forms that no artist could have designed. Forms that are partly random and partly governed by physical laws, partly chaotic and partly exquisitely structured. The Eagle Nebula, located about 7,000 light-years from Earth in the constellation Serpens, contains a structure called the Pillars of Creation, towering columns of gas and dust that extend several light-years in height, their surfaces sculpted by the radiation and stellar winds of nearby young stars, glowing golden orange at their edges and dark and dense within, their interiors hiding the earliest stages of new star formation. The original Hubble Space Telescope image of the Pillars of Creation, captured in 1995, became one of the most widely recognized astronomical images ever taken, printed on posters and book covers and screensavers around the world, carrying the cosmos into living rooms and classrooms in a way that no amount of scientific description quite could. When James Webb later captured the same region in infrared light, it penetrated the obscuring dust and revealed details hidden for decades. Embedded protostars in the act of formation, glowing warmly in the infrared, stellar embryos gathering mass in the dark interior of the pillars, preparing for the ignition that will eventually light them up. The Crab Nebula is the expanding remnant of a supernova explosion that was seen from Earth in the year 1054. Chinese astronomers recorded the appearance of a brilliant new star in the constellation we now call Taurus, so bright it was visible in daylight for about 3 weeks, and in the night sky for nearly 2 years before fading back into invisibility. Native American rock art may also record this same event, a bright point of light near the crescent moon, depicted by people who had no knowledge of what they were seeing beyond its undeniable presence in the sky. At the center of the Crab Nebula today is a pulsar, the collapsed remnant of that ancient star's core, spinning 30 times per second, its rapid rotation sweeping beams of electromagnetic radiation through space like a lighthouse. The nebula itself continues to expand outward at about 1,500 kilometers per second, a visible echo of an explosion that happened nearly 1,000 years ago, still growing, still spreading the enriched material of that star's life through the surrounding space. The Orion Nebula, visible to the naked eye as a faint, fuzzy patch in the sword of the constellation Orion on a clear winter night, is one of the most active star-forming regions within relatively close range of our solar system, about 1,400 light-years away, close enough to study in extraordinary detail. Within it, dozens of young stars have formed in the last few million years, many of them surrounded by protoplanetary disks, flattened rings of gas and dust from which planets are currently forming. Solar systems in the process of being born. When you look at the Orion Nebula, you are looking at something very like what our own solar system may have looked like 4.5 billion years ago, before the planets had fully formed, before the Sun had settled into its long middle age. You are looking back at a version of our own beginning. Now I want to talk about time, because this is perhaps the most quietly extraordinary aspect of looking at the sky, and the one that, if you sit with it long enough, has a way of dissolving the boundary between the present moment and the vast ancient past. When light leaves a distant object and travels toward us, it takes time to make that journey. Light travels at about 300,000 kilometers per second, the absolute speed limit of the universe, the fastest anything can move. But the distances in space are so enormous that even at that speed, light takes years, centuries, millennia, billions of years to reach us from some sources. The Sun is about 8 light minutes away, meaning that the sunlight reaching Earth on any given day left the Sun about 8.5 minutes ago. When you look at the nearest star beyond our Sun, Proxima Centauri, you're seeing it as it was 4 years ago. The Andromeda galaxy appears to us as it was about 2.5 million years ago, before our species existed, before most of our genus existed, when the first stone tools were just beginning to be made by distant ancestors, whose brains were smaller and whose lives were incomparably harder than ours. When James Webb looks at the most distant confirmed galaxies, it is detecting light that has been traveling since the universe was less than 400 million years old. The night sky is not a view of the present. It is a mosaic of different pasts, all arriving at your eyes simultaneously. Different layers of cosmic history overlapping without distinction in your field of view. A star 10 light-years away and a galaxy 10 billion light-years away appear side by side in the sky, but they represent moments separated by nearly 10 billion years. You are seeing, all at once, the universe at many different stages of its life, its infancy and its middle age and its current moment, all compressed into a single glance upward. And here is the deepest part of that thought. We can never observe the universe as it truly is right now, in this very moment, across its full extent. The speed of light is a finite speed. Every observation we make is a message from the past. The universe we study is always a portrait of what was, not a window onto what is. We are cosmic archaeologists, reading the light that ancient sources sent into space, catching it after its long journey, and reconstructing from it the story of a universe that has moved on since these messages were sent. The galaxy whose ancient light James Webb recently captured has aged another 13 billion years since that light departed. We're seeing its childhood while it exists, somewhere out there in the present, in an old age we cannot see. There's something almost tender about that. The universe keeps records. Every photon that reaches us is a letter written long ago and delivered faithfully, unchanged, across unimaginable distance. Light does not age during its journey. It does not forget what it was carrying. It arrives after billions of years of travel, still bearing the exact information it was given at the moment of emission, still telling the story of the star or galaxy that sent it. The cosmos remembers. Let's return to the galaxy that shouldn't exist, because I want to sit with what it truly means, not just as a scientific puzzle, but as a kind of gift. What the James Webb Space Telescope found is a reminder that for all of our knowledge, for all the centuries of observation and mathematics and elegant theory and careful experiment, the universe remains genuinely larger than our current understanding of it. Not in a frightening way, in a generous way, in the way that an ocean is larger than any single map of it. And that largeness is not a problem, but a promise. The promise that there is always more to explore, more to discover, more to be surprised by. We have mapped extraordinary amounts of that ocean. We understand the tides and the currents, the chemistry of the water, the behavior of light as it descends through the depths and fades into darkness. We have sent our instruments to extraordinary distances, but the ocean keeps going. And every now and then, from somewhere in the deep, something rises to the surface that doesn't fit the charts. Something that says, the map is not the territory. Keep sailing. You haven't seen everything. These impossibly early galaxies are that kind of message. They are the universe extending an invitation, saying, in the only language it speaks, light, gravity, time, that the story is still unfolding and that the next chapter may be the most interesting one yet. As you breathe now, slowly and without effort, perhaps feeling the comfortable heaviness that comes with late hours and warm stillness, the world around you growing softer at the edges, I want to take you somewhere very quiet for a while. Imagine floating in space, far from any galaxy, in one of those great intergalactic voids. No sun, no planet beneath you, no atmosphere to carry sound, just the cold and the dark and the silence, and all around you, at immense distances in every direction, the faint glow of galaxies. Some are spirals, their arms curving gently. Some are ellipticals, smooth and warm. Some are in pairs, their gravity pulling them into slow, majestic collisions that will take hundreds of millions of years to complete, their spiral arms distorting and stretching toward each other in immense tidal streams of stars. All of them moving, all of them aging, all of them full of stars and worlds, and the long, patient chemistry of the universe working its way toward forms of complexity we've only barely begun to map. And you are floating in the middle of all of it, not lost, not adrift, held by gravity, by the simple fact that you belong to this universe as completely as any galaxy does. You are made of its material. You are governed by its laws. You are continuous with it in every physical sense. The void is not empty. It is full of the fabric of space itself, full of the invisible dark energy that stretches it gently outward, full of dark matter flowing in slow rivers between the visible structures, full of photons from countless sources crisscrossing in all directions, carrying their ancient messages through the dark. Let me tell you a little about dark matter and dark energy now, because they are perhaps the most mysterious characters in this cosmic story. Present everywhere, essential to everything, and almost entirely unknown. The ordinary matter that makes up stars, planets, gas clouds, dust, you and me, everything we can see, touch, or measure directly, accounts for only about 5% of the total energy content of the universe. 5%. All the stars, all the galaxies, All the nebulae and black holes and planets and moons and asteroids and comets and gas clouds and you and every living thing that has ever existed. All of that is 1/20th of what's out there. The remaining 95% is something else entirely. About 27% is dark matter. We know it's there because of its gravitational effects. It bends light in ways that only mass can explain. It holds galaxies together from the outside in ways that visible matter alone cannot account for. It determines the rotation curves of spiral galaxies. It provides the gravitational scaffolding around which the cosmic web is organized. Without dark matter, galaxies as we know them could not exist. The Milky Way, the Andromeda Galaxy, every spiral and elliptical in the observable universe, all of them are embedded in vast halos of dark matter that extend far beyond their visible edges, invisible but essential. And yet, in decades of searching, with some of the most sensitive particle detectors ever built, placed deep underground to shield them from cosmic ray interference, we have never directly detected a single dark matter particle. We don't know what it is. It may be a new type of particle that we haven't been able to create in a particle accelerator yet. It may be something stranger, primordial black holes left over from the Big Bang, or something we haven't imagined yet. The name dark matter doesn't describe what it is. It describes our ignorance of what it is. And that is a remarkably honest thing for a scientific term to admit. And the remaining 68% is dark energy, perhaps even more mysterious, even more fundamental, even more resistant to our current understanding. It is a property of space itself, apparently, that causes the expansion of the universe to accelerate. The universe is not just expanding. It is expanding faster and faster over time. The galaxies are moving apart at increasing speed, and the cause is something that fills empty space uniformly, that has no mass, that doesn't thin out as the universe expands, but maintains a constant energy density throughout all of space at all times. We call it dark energy because we don't know what it is. We have an equation that describes its effect, the cosmological constant, which Einstein introduced into his equations over a century ago, and later called his greatest blunder before it turned out to be correct after all. But the equation describes what dark energy does without explaining what it is or where it comes from. Why does empty space have energy? Why that particular amount? Why does it cause acceleration now in this epoch of cosmic history rather than earlier or later? We don't know. And that is one of the most active frontiers in all of physics. So the universe, in its totality, is about 95% mysterious. And rather than being unsettling, I find that deeply reassuring. The mystery isn't going anywhere. There will always be more to learn. The universe is inexhaustible in its depth, and that means the conversation between human curiosity and cosmic reality will never end. Every generation will have its own James Webb, its own instrument that sees further and more clearly than anything before it, finding new things that don't fit the current map, calling for a more complete one. The story is open-ended. The last page has not been written. Before we sleep, one last thought to carry with you. The universe will not last forever in its current form. In the very long run, across timescales almost beyond the power of language to express, things will change. The last stars will eventually exhaust their fuel and go dark over a period of trillions of years, a duration more than 100 times the current age of the universe. After the stars are gone, black holes will dominate. scattered through the cold, dark universe, slowly orbiting each other, occasionally merging, the last large-scale events happening on timescales of quadrillions of years. And even black holes, according to a theoretical process called Hawking radiation, first described by Stephen Hawking in 1974, will gradually evaporate over timescales measured in numbers with 100 zeros in them, releasing their mass back into space in the slowest possible trickle of energy. Eventually, the universe may reach a state of maximum entropy, maximum uniformity, maximum disorder, where no further work can be done, no temperature differences remain to drive any process, no further structures can form or persist. A final stillness, the deepest possible rest. But that is so incomprehensibly far in the future that it exists not as anything to mourn, but as the last line of a story that will take longer to conclude than we can truly feel. Right now, the universe is young. It is, by most estimates, not even halfway through the era in which stars exist. Right now, somewhere in the universe, new stars are igniting for the first time. New worlds are cooling from molten rock to solid ground. New oceans may be forming. New chemistry may be organizing itself toward complexity in ways we'll never know about. The universe is still in its creative period. It is still becoming, still finding new arrangements, new structures, new forms for matter and energy to inhabit. And you are one of those forms, perhaps the most intricate and self-aware that we know of, even if we suspect there may be others. So, here we are, you and I, and the universe stretching away in all directions beyond the walls of wherever you are right now. The galaxy that shouldn't exist is still out there, billions of light years away, still burning with the ancient light it made at the very beginning of cosmic history, still teaching us something we didn't know before. The black holes are still turning at the hearts of their galaxies, patient and immense. The nebulae are still quietly building new suns from clouds of gas and dust. The cosmic web is still slowly shifting, its great filaments drifting in the dark over timescales that make civilizations look like flickering candles. The universe is awake and busy and beautiful, and it will still be all of those things long after tonight is over, long after any of us are here to observe it. And you are still here, still breathing, still part of all of it. I hope tonight's journey through the cosmos has given you something soft to carry with you into sleep. A sense of scale that makes the worries of today feel smaller, held inside something vast and patient and ancient. A sense of wonder that feels like warmth rather than overwhelm. A quiet sense of belonging. Not earned, not fragile, not dependent on anything you've done or haven't done. Just the simple physical fact that you are here, in this universe, made of this universe, and that you have been part of it for far longer than this single life would suggest. Thank you for spending this time with me here on Dreams of Gravity. It means more than I can say. Close your eyes if they aren't already. Let the stars drift slowly behind them. Let the galaxies keep turning in the dark without your help tonight. Let your breath keep coming and going on its own. Let the universe do what it has always done, expand and burn and age and form new things from old materials. While you rest, it knows what it's doing. It has been doing it for 14 billion years, and it will still be doing it tomorrow morning when you wake. Good night. Sleep softly. Dream well. And somewhere out there in the dark, the galaxies are turning, slow and silent and impossibly beautiful, just for the pleasure of it.